Okay, so when you do the exam, not next week, but the week after that, I hated time pressure on an exam. So by having 2 hours and by having an hour exam, that'll usually, you can get through fine without going insane trying to figure out what to do. Usually takes about 20 minutes to a half hour to have confidence to hand in your exam. So at some point, you have your exam all done. And then there's actually then a mental click that has to, mental state that has to change in your brain where you feel like you can actually hand it in. So you have this done and you're going to hold this in your hand, but looking through all the problems again and again and again, thinking, is it safe to hand it in? At some point, you just realize I'm done, and then you're just hand it in. What I do is next week sometime, I will hand out the exam I gave the previous year. I will not give solutions because who creates the solutions? You are your own solution. Okay, you can work it out and you can stop by my office and I'll go over your solution with you. Okay, but I'm not going to hand out solutions. Otherwise, what you're going to do is you're just going to work to get the solutions, and I want you to actually beat through it by yourself. The other thing is that if you show me the exam and if it's blank, I'm not going to help. Okay, I want to see where you, because it's not going to help. That's why I'm not trying to be mean, but it's just not going to help you. The whole act of trying to go through it, you're going to learn a lot. And you can get together with your buddies and stuff like this and crank it out. That's fine. But I want you to actually try the exam by yourself. The way I give the exams, there are two parts to it. I call the first part one, kind of clever. Okay. So part one, these are going to be 6 shorter problems. Okay, you're going to do any 5. We're going to need 5 of the 6. You can do the question you didn't do as a bonus question. Just kind of know that is your bonus question. Okay, now here's just some test strategy. If you have 6 questions to do, but you only have to do 5, and 1 is a bonus, what would you not do with the question you didn't answer?
Not do it fully.
Yeah, well, you would not leave it blank. Okay, if somebody is offering you free points, okay, you do not say, no, thank you. I do not need them. That is just test-wise, that's just being, okay. It's even better to write Baba Black Sheep have you when you will, yes, sir, 3 bags full. That's certainly better than leaving it blank. Okay, so, at least attempt it, because I will give, let's say you do a bonus question, and let's say it's screwed up, but there's some aspect there that is right. I will give you partial credit for the bonus. Okay. There will be no plug and chug. So I wouldn't have something like, delta x equals 2, delta t equals 3, find average velocity. Oh, delta x over delta t. This is 2 over 3. There's my answer. You will not have anything like that. That is just a stupid question. There's no point in asking you a stupid question. There'll be something where you have to think about. And then part 2. And these will be 3 longer questions. And you do all 3. Okay. And these are going to be on the main ideas in the class. So what are some of the main ideas we've had so far? Close. Very close. Okay, like adding vectors and things like this. So there's probably going to most likely be like one big adding vector problem. Okay, we're going to start projectile motion. That'll be on the exam. There's obviously going to be a big projectile motion question. And then we've had things like, if I give you an acceleration, you should be able to find the velocity. If I give you the velocity, you should be able to find the position. Things like that. Kind of the big ideas. Okay, that makes sense. Questions? And that'll be the format for all 3 exams we have. Okay, questions? You can't make up exams, so there's always been people who have tried to challenge me with this. They magically get sick, just usually like an hour before the exam, and just can't make it, and that does not go well. Okay, I do not recommend that. Okay, any questions? Okay. Okay, so we're starting in 2D motion today. And once we're done with that, that'll be the last topic on the exam. Yes.
I assume we're not having a lab during that time.
Yeah, we're gonna have a lab at the same time.
All right.
Okay, so you have the lab set up and your exam, and you have to go back and forth between the two. No, that'll be.
Too much?
Yeah, that we will not do
Okay,
that.
cool.
Although now you got me thinking, maybe.
I mean, yeah, maybe after we could do the lab.
Yeah, maybe we'll do that. Maybe the lab will be part of the questions. That'd be cool. Okay, so we're gonna do 2D motion. Okay, this is the off semester physics. You know, the big section of general physics is in the spring for physics 125 and in the fall for 126. Those, since I can't do it in the lab because I have such a big section and there's multiple lab sections, what I do with that is that then I have the exams in the evening. So if you're in the on section, meaning the big section, we'd have the exams on Thursday evening. And they'd be from like 6 to 9 or something like that. That's what I do with that. Dinner room. But this isn't that case, so you don't have to, there won't be here in the evening. Okay, so this is gonna be basically, this is gonna be motion in both the X and Y directions. So we're gonna have a Y-axis here. We're gonna have our X-axis here. And we're gonna have some object that makes some path. So this is the path of the object. Okay. And so the question is, how do we analyze it? So first of all, for the rest of your life, the position vector is going to be R. So we need a position on here. So the position of the moving object is called R. Some books will have S, but usually R is the more standard one. So we're going to use R basically in general physics. So for upper level physics courses, it's going to be R. I think even the engineering courses, they probably use R as well. So if I had a position here, let's say the object is here. That's R. You tell me how we'd write that. I want to write it in terms of X and write it in terms of Y. Meaning that if I go here, if I drop my perpendicular, this is my Rx component, but I'm going to call the Rx component just X. Okay. And this right here would be my Ry component. And just the Ry component from now on is just going to be Y. You tell me how to write that vector then. I could write R vector as, and you're all pros at this. Okay, tell me how to write a vector in terms of unit vectors. So put it all together. So this vector here would be X I hat. And what would you add to this vector? You'd do a tip to tail fashion. You'd then add this vector, which is Y j hat. That makes sense? Okay. And sometimes what you'll see is that these are functions of time. So I can say this R is a function of time, this X is a function of time, and this Y is. It really means this right here. I'll probably write it like this and just assume that the time dependence is implied, because this is just too hard to write. So we're going to do something easier. Okay, so let's go through and do this. So here's our object. I'm going to say this right here. This is my position vector at point 1. So this is at T1. So that's at T equals T1. So the object's here. A little bit later on, the object's here. So this is at time T2. And this is my buddy R2. Okay. What distance did this object travel? What's my delta R here? But I say graph it. What vector do I have to add to here to get this vector here?
Vector G.
Okay, and how would it look? Put a draw it in there. From the tip to tip. So from here, this distance right here, that's my delta R vector, right? Because if I take this vector here, if I take R1, if I add delta R to this, that's my change in R. That has to be equal to this vector here, R2. That makes sense? What I can say is that this R2, final vector, it's R1 plus my change in R. So my R is nothing but R2 minus R1. And that's nothing but saying what? What is a change always given by? Always, always, always. A final minus initial. So here's my final R minus my initial R. And that's my change in R. Does that make sense? Questions? Okay, now if I want then the average velocity of this. Hey, what do you think you do then? This is where physics is great. In physics, I always say that physicists are one-trick ponies. You learn a trick and then you beat that trick to death. Okay. So extend what you know about in one dimension to here. How do you then define the average velocity for that object then?
Delta X and delta T.
Now put in these variables, delta
R.
R over delta T. And it's a vector, so this is going to be delta R and delta T. Okay, does that make sense? Hey, but suppose I want to know how fast the object is going here. What would we do? Okay, put in the mathematics and we'll analyze that. Because it's going to be right, but it's going to be a little slight variation. Not much of a variation. Everything you said is true. So, go through the thought process to get this. Again, extend what we did in one dimension. Remember, in one dimension, we had the average velocity is delta X over delta T. Then how did we get the actual velocity? What did we do to our delta T? Smaller and smaller and smaller and smaller. And what is mathematically we say we take the limit, which then gives us the derivative. So mathematically, what we say is that, I'm going to say the actual velocity is going to be the limit. Is this delta T goes to 0, this delta R vector or delta T. And this is by definition, this is our dr vector over dt. Does that make sense? So what happens here, if my delta t's become smaller, this one here moves here, and it moves here, then it moves here, then it moves here, then it's some tiny little distance away. So if I were to draw that, I'd get this. So here's my R here. I'll call that R1. I'm taking this value here, and then I'm moving it to here, and then I'm moving it to here, like that. I keep on taking this point here, I take that time and I make it smaller and smaller, make it closer and closer to this point here. So at some point, this little distance here, that becomes my delta R. Does that make sense? Well, if I keep on doing this, what can you tell me about that delta R vector then? That delta R vector is then, now going over the thing, is going to be tangent to this curve at this point here. Okay, so this velocity here, this is going to be the V, is tangent to the Y versus X. Okay. If I had an object like this, so I had this object here. Okay. What would the velocity have to look like here? It's going to have to be tangent to this graph, right? That's my velocity here. And right here, how would the velocity look there?
Less.
It's gonna be less and it's gonna be tangent to this graph here. What about at the very tip? Yeah, it's gonna go like this. If I'm here, and like that. Okay, it's always gonna be tangent to this graph here. Does that make sense? And again, it's entirely because of the fact that this delta R goes from this point to this point. And if I take this point here and move it closer and closer and closer and closer to this point, that little delta R then becomes tangent to that little section right there. That makes sense? Okay, so what does that mean? Let's put in all the bells. Any questions with that? So what does this mean? So say my velocity is dr dt. Hey, what did we say R vector is? R vector is always x I hat plus yj hat. Now, this x on here, so this gives me dx dt, I hat, plus dy dt, j hat. Okay. Does dx dt have a name? That's going to be the velocity in the x direction. So I'm going to call that v sub x. So this fellow over right here, this is v sub x, I hat. Plus, this value here is
Velocity.
the velocity in the y direction. Does that make sense? Hey, how do you think I'm going to define the acceleration? It's the exact same thing. Okay. And so what we have is that, so to find the acceleration, we start with the average acceleration. You tell me how this is going to be defined. Again, physicists are one-trick ponies. You take what you know, you extend it. Change in v, and the v is now going to be a vector. I mean, it was a vector before, but now we really have to worry about the two dimensions of that. Over change in time. Hey, then how are we going to get the actual then acceleration? What are we going to do with our friend delta t? Make it smaller and smaller and smaller. And so the actual velocity is the limit as delta t goes to 0. This quantity here. Exactly what we did in one dimension. Okay. Now, hey, what do you think we're going to define this to be then? That's nothing but our formal definition of derivative of the velocity here. So this is going to be dv dt. Okay. Talking about the velocity then. How can I write this velocity here? Vxi half plus vyj half. So what is this? This is A equals dvx dt I half plus dvy dt j half. Hey, do you think dvx dt has a name? What might that be? Acceleration in the x direction. Hey, well, my TV, YD TV. Acceleration in the y direction. And if you had a, in this class, we're not going to worry about 3 dimensions. But if you're a mechanical engineer, you're going to worry about 3 dimensions. Okay, and if you take upper level physics courses, you're going to worry about 3 dimensions. But in this course, not so much. And if you had a 3rd dimension, what do you think you would do with this? I'll give you a hint. Again, physicists are one-trick ponies. You find a trick, and you beat that trick to death. This is why in physics, you have to know remarkably little. But the catch is, what the little amount you have to know well. Then you extend it. So, if you're an engineer, what might you also have in this here? Your velocity is going to be plus the VZK hat. When you put this in here, it's going to become the AZK. In this case here, we're just going to have the AY. There, that's it. There is nothing else to know about 2D motion. So all we're going to do for the rest of the day are examples, and all we're going to do on Monday in class are examples. And then in lab, we're going to do projectile motion, which is fun. And then once we're done with that, that'll mark the end of what's covered on the first exam. So the first exam will end after we've done a whole bunch of examples of this. Okay. Question?
Are we going to spend next week reviewing or learning the material?
We're going to learn new material. I do remarkably little review because you're all grown up. Okay, you're an adult here. You can.
I was not coming here, I'm kind of behind with the show.
Okay,
I was
so
right back.
I just put it there. Okay. We started off with a moment of silence. They had a moment of silence. Then people stood up and talked about Zalif, what Zalif meant to them. Then we had a poem dedicated to you. It was called Ode to Zalif. Okay. Then we had a little song. Okay. That went to the tune of Gilligan's Island, because all good songs should go to the tune of Gilligan's Island. Okay. Questions? Let's do examples. Okay. So let's say I have an acceleration, and I'm just going to make something up. I'm going to say that this is 5 t I hat plus e to the, let's say 3e to the minus 5 t j hat. And let's say the initial velocity for this is 2 I hat plus 3 j hat. The initial position for this object is I hat plus 4 j hat. Part A. What do you think part A is going to be? What? What did you? This is okay. This is a B, although it doesn't look a whole lot like a B, and this is an R. Right.
Oh.
Try doing that with PowerPoint. Ha! They don't have the finger of power.
Why does it have to have the little vector symbol?
You tell me.
Mm.
But we didn't when we were doing the 1D part, but now we're putting on the vector symbol here. Why don't you do this? Because if you have it like this is really the magnitude. And this is the vector, because you can see the I hat and the j hat here. So when you have an actual vector like this, go like this. If you're to do this, this is the same thing as saying this, which is really going to be what? That would really be the 2 squared, 3 squared. Okay. Again, right now it seems like a fine point. I think, well, who cares? As you do more and more advanced things, it turns out to make a really major difference. Okay, so try to, if you're sloppy with notation, try to get good notation. It's going to make a big difference when you take more advanced courses. And plus, when your professor is grading your work, you want them to look at it and say, look at this. All these vector symbols exactly where they are. And they'll put it on their little refrigerator at home. Well, Errol, this is my student. Maybe not, but still you want to use good notation. Okay, so what is part A? We're gonna find. Think about what we did in the 1D case. If I give you an acceleration like this, what was always part A of this? Find the velocity. So this is gonna be find. You like this as the function of time. Hey, what do you think part B of this is gonna be? Which is gonna be our R vector. So this is gonna be find our R as a function of time. There's no difference from what we did before, except now we have to do it basically twice. Okay, so let's start. Does this have a name here? 5t. And this is my A vector. That 5t is nothing but our buddy AX. Hey, does AX always equal something for the rest of your life? Yes. Be now more fussy. dvx dt. Okay, and so this is going to be 5t equals dvx. Hey, do we know how to solve that? Yes. What do we do? Take the dt over. And integrate it. Tell me about the time. Where does time go from? It always starts at 0, goes to generic time t. Now, from this problem here, tell me what the limits on Vx are.
Two,
Come on.
two,
Eh,
two plus three.
Okay, 2 to V x. Okay, so if we look here, what is the name for this? This is my initial velocity here. Okay, so this is V naught x. And this right here is V naught y. Whether I put the 0 and the x up or lower doesn't really matter. I'll probably be inconsistent myself. Or whether I put them both lower or both upper, I'll probably be remarkably inconsistent. Okay, so this has to start at a 2. And then what does it go to if I want a generic expression? Vx. So this left side B gives me what? Five t squared over 2. Do I have to worry about the upper and lower limits there? I do, but what's going to happen is just becomes this. So I'm going to be sloppy. Now tell me about the integral of dvx. That's vx. Now do I have to worry about the limits? Yes. Because this one down here isn't a 0, it's a 2. So this is, I'm going to put the 2 in the vx here. So this is going to be vx minus 2. Or put it all over here. Okay. Half done with that part. Hey, what do we have to do next? The same thing with y. So we come over here. So we're going to repeat for vy. So I'm going to say ay is always dvy dt. My ay is over here. This is my ay. Hey, what do we do with that?
Takes the.
Take the dt and repeat the procedure. You tell me the limits on that on those integrals. Oh, and I see, notice what happened due to the limited blackboard space in the Science Center. I was forced, okay, to erase my buddy V naught. Okay, so what was my buddy V naught? 2 I hat plus 3 J hat. Sorry about that, buddy. Okay, you tell me now what the limits are for my integral friends. The left is going to go from, yeah, my initial V, this is my V naught Y. This goes from 3 to V,
What?
Vy. My time,
0 to
0 to 2. Tell me about the left side. And this is going to be Vy evaluated from
3 to
3 to Vy equals, Notice, I can't stop myself. I'm being forced to erase it for or not. That one happened in Olin. Plus, we'd also know what the stock market is. Those tragedies in life. Tell me about my buddy on the right. What is that in? Negative 3 over 5. Done. Now, what can you always do with integrals that you can't do with derivatives? You can always check them. So when you do this, okay, this is correct. But let's say you didn't know. So what would you do if you differentiate this? How do you differentiate an exponential? First of all, what happens to the exponential by itself? It always comes down to this. So let's do a little checking. So now you differentiate an exponential. Okay, the constant comes along to the right. So this constant I'm just carrying over here. The exponential is great because the exponential always comes along to the right. Now, what do you put in front? Well, the derivative of this with respect to t. The derivative of the exponent with respect to t is just minus 5. Minus go out, the minus signs go out, and that gives me this, and this again is called the integrand. So you should recover that integrand. Okay, if you don't, then it means there's a mistake. But always, again, this one here you can kind of do in your head once you get accustomed to it. You can start getting really more complicated things, which are not, they're really quite tricky. Again, integrals are hard. And grad school, I remember there was one time I did this really involved calculation. It was this involving an integral. I showed it to my advisor. Before I could even say boo, he went, "That's obviously wrong." That took me a while to figure out how he was doing that. And he was using a trick that you don't know yet, but he was doing a trick, and very, very clever trick because he was a very, very clever man. But these tricks come with time. And you too, at some point, if you go on with more things, you will learn these tricks. Okay. Okay, so let's go through and evaluate this. What does this side over here become? Vy minus 3 equals. Okay, the upper limit gives me this, minus 3/5 e to the minus 5t. Am I done with my expression there? No. How come? Because that stupid lower limit doesn't give 0, actually contributes, right? Because when you put in the lower limit, when you put a 0 here, e to the 0 is 1. Okay? So you have minus this guy here. Here, like that, and that gives me 1. So this gives me minus 3/5 e to the minus 5t plus 3/5 Vy minus 3. Take this over here. Okay, would you leave your answer like that? Please, please, please say no. Okay, what would you do? Get a common denominator. Also, don't write this as a mixed numeral. Don't give me, 3.6. Never use mixed fractions or decimals in equations. Always get a common denominator. Okay. Common denominator would be a 5, so I multiply top and bottom here by 5. This is the 15. 15 and 3 is 8. So this is minus 3/5 e to the minus 5t plus 18 over 5. I'd probably do one more thing. If those are more advanced calculations. I do one last check on this. What would be my check? I know this value has to be at one particular point. At t equals 0, that velocity better become my initial velocity. So if I put in t equals 0, do I recover 3? I put a 0 here. E to the 0 is 1. So minus 3/5 plus 18 over 5 is 15 over 5. 15 over 5 is 3. So that would recover. Always check your values. You just don't, people sometimes will put things in their calculator and get something and they'll say, well, this is what my calculator says. I don't care. I could care less what your calculator says. It's wrong. And this is where you have to actually turn off your calculator and actually reason. Okay, that makes sense? So that means our velocity then, as a vector, if I want the equation, there's going to be this fellow here. I hat plus my buddy here. It looks ugly, but ugly is allowed. Okay. Does that make sense? Now, I won't go through the whole thing. I'll just set it up for you. That's part A. What was part B?
Fine.
Find the position. Okay, you tell me how to proceed. So part B is fine. R is a function of time. Again, R is going to be your position for the rest of our life. And the reason we use R is that position starts with the letter P, therefore we use the letter R. That's a joke. It's not necessarily a funny joke, but nevertheless, it was a joke. Tell me how to proceed. I'll give you a hint, you're all pros at this. In the words of Scooby-Doo, what would be? Ring, ring, rag. You're mastering Scooby-Doo and you're not even done with the class. Okay. So tell me how to do this. I'd say my buddy here is, I know that this is nothing but my friend Vx. But does Vx equal something else? Vx always now has to be dx dt. And then you take the dt over. Then you integrate this. Where's your time going to go from? 0 to t. Where's your x going to go from? And notice I was forced to erase that position due to the limited Blackboard space of the science center. Although the science center is getting a major refit in a couple of years. The architects are actually designing it, and I think that they're knocking down walls, redesigning things. I'm probably going to lose my brand new shiny office that has light, which makes me cry. But the building will be better. I'll take one for the team. But that's not for a couple of years now. So hopefully there will be more Blackboard space. I might lose out on that argument. But that's okay. I'll ultimately win. So what did we say about R naught? R naught was what? Yeah. So this was 5 I hat? Is that right?
No,
Just I hat, and then this is 5?
that's forward.
There's no 5 at all. Okay. Okay, so what do you have then for this? Give me the limits. 1, 2, x. Okay. You can go through and do that yourself. Let's set up the y. I said then Vy is my friend over here. Vy is always what for the rest of your life? the dy dt. You repeat the process. Okay, what would be my limits on this guy? Yeah, this would be, the time always goes from 0 to t. Again, this one's going to be easy, but again, this one here, you're going to have to remember the lower limit when you evaluate it. Limits on this one? 4 to 1. Does that make sense? Okay. Again, if you have 3 dimensions, which it turns out when you take upper level engineering courses, you will. Upper level physics courses, you will as well. Eventually what happens is, well, what do you would you worry about in physics? Where might you worry about 3-dimensional motion? Let's say you want to study the atmosphere. So you have these computer models for the atmosphere. These are all 3-dimensional models. Let's say you work for the military and you want to launch long-range missiles. Okay, what do you then have to start accounting for? And even in weather systems, what does the Earth do? It rotates. And so when you do that, you have to start worrying about things called Coriolis force, which turns out that it's going to actually, from our point of view, it appears actually when you launch something in the northern hemisphere to deflect things to the right. So what you find out that if you're if you're in the northern hemisphere, if you launch something to the right, it's going to kind of go like that, which is really kind of neat. Okay, it flips in the southern hemisphere. You can find out if you take more orthogonal physics courses. Does that make sense? Now we're going to go through a special case. I'm going to take the special case where the acceleration is a constant. So let's ask what happens if you have constant acceleration. So what happens?
Wait, so well, we could just leave it as the 2.
Okay, so what I would, if I were to solve this one here, right, this would give me y. Value it at 4 and y. So this would give me y minus 4. And this, I would work out this guy here. I take this over here, that would give me y. I do the same thing for x. And then I'd ultimately then say, R is going to be xi hat, and this will be the mess that you're going to put in from your result there, doing that, and then plus y j hat. And so you solve this with y, it's going to be the mess, and you put that one there. That makes sense? Good. Okay, so what happens when a is a constant? So you're going to say a equals ax I hat plus ay j hat, and both these values here are constant. Hey, I think you're pros at this. You tell me exactly what to do. You don't even need me here, right? I'm going to say the initial velocity is v naught x I hat plus v naught y j hat. And again, whether where the x and the naught are, it doesn't matter whether they're up or down. I will not be consistent. And the initial position is x naught I hat plus y naught j hat. You tell me exactly what to do. We'll start this up and we'll call it quits. So we'll finish this discussion on Monday, and that'll be projectile motion. And that lab we have on Monday, we're going to be using these equations. Let's just give a push here. We'll call it good. What do I do with AX? That's going to be, what is AX always? The rest of your life? What? dvx dt. And I'm going to say AY is going to be dvy dt. Let's do this. We'll just do this one and we'll see what we're going to do. So this would be AX dt. equals dvx. Where does that one get integrated from? 0 to t. This one?
X to X.
Perfect. V naught x. Dx. The ax is a constant. This comes out. The integral of dt is t. This gives me vx, evaluated at v naught x. Vx, which is vx minus v naught x. So this tells me that vx equals v naught x plus axt. Hey, does that look familiar? When we had 1D motion, remember I said there were 3 equations always valid. What was the one for the velocity? V equals v naught plus at. Hey, this is exactly the same thing, but we just now have the x components. Hey, what do you think is going to happen for Vy? Vy is going to be Vy equals
You know.
V naught y plus
They were.
ayt. Yep. And the positions are going to be the exact same thing, and we'll go through that. And once you get that, there's nothing else to do with projectile motion. We'll apply it. We'll see kind of fun things. I'm gonna teach you about snowball fights. Okay, when you're a kid, and you're in a snowball fight, your buddy's over there. What do you want to do? You want to hit your buddy in the head with a snowball because you're a kid, and that's what kids do. Okay, when you want to hit your buddy with a snowball, how do you throw your snowball? You know this as a kid, you just haven't thought about it. There are 2 angles. There's a high angle and there's a low angle to hit your buddy. I want to show you why that's the case. And so there's 2 angles. There's one you can throw high and hit your friend, one a low angle you can hit your friend. Okay, yes. So this R naught is x naught I hat plus y naught j naught.
Oh, why?
Okay. Have a great weekend.
It's not there. So my building.
Yeah.
See, that was good. Yeah, it's on that.
Take care. You as well.
I smell forward.
She was like.